If you thought the latest images from the James Webb Space Telescope were impressive, what you're about to see may completely change the way you look at the universe. A new space telescope has been quietly surveying the cosmos on a scale we've never attempted before. Its name is Euclid, and instead of focusing on a single spectacular object, Euclid is designed to reveal the enormous structure connecting billions of galaxies. The images are beautiful. But what they represent is even more remarkable. Euclid was launched by the European Space Agency in July 2023 and sent toward the Sun-Earth Lagrange point L2, roughly 1.5 million kilometers from Earth. From there, it can observe enormous areas of the sky while maintaining the precision needed to study individual galaxies. And Euclid has a very different mission from Webb. Webb is designed to investigate individual galaxies, stars, planets, nebulae, and some of the earliest objects in the universe. Euclid is taking a much wider view. Its goal is to understand how galaxies are distributed across cosmic space and how that distribution has changed over billions of years. But there's something even more fascinating. Euclid isn't simply photographing what we can see. Scientists are using tiny distortions in the shapes of distant galaxies to investigate the invisible mass between them. This technique is called weak gravitational lensing. Gravity from massive structures bends the path of light. Dark matter doesn't emit or reflect light, but its gravity still affects everything around it. By measuring incredibly subtle changes in galaxy shapes across enormous regions of the sky, astronomers can reconstruct the distribution of dark matter. In a sense, Euclid is helping scientists create a map of the invisible architecture of the universe. One of Euclid's early releases demonstrated just how enormous this project is. The telescope produced a mosaic containing hundreds of images and covering a huge area of sky. Within that enormous field were millions of stars and galaxies, many of them appearing in extraordinary detail. And this is only a small fraction of the survey Euclid is expected to complete. That is what makes these images so important. They are not simply pretty space photographs. They are pieces of a much larger scientific map that will eventually help researchers study the universe in 3 dimensions. Look closely at the galaxies and another pattern begins to emerge. Galaxies are not distributed randomly. They gather into clusters, stretch along enormous filaments, and surround vast regions known as cosmic voids. Together, these structures form what scientists call the cosmic web. The scale is almost impossible to imagine. Some of these filaments extend across hundreds of millions of light years. Galaxies move within a gravitational environment shaped by dark matter, while enormous empty regions separate the densest structures. From a distance, the universe can look almost like a giant network. But that network isn't made of solid material. It is the large-scale distribution of matter, with dark matter playing a crucial role in shaping where galaxies eventually form. Euclid is particularly valuable because it can measure these structures statistically across huge areas of sky. And the larger the sample becomes, the more accurately scientists can test their theories. One of the major targets is dark energy. For decades, astronomers have known that the expansion of the universe is accelerating. The simplest explanation is a component called dark energy, but its true physical nature remains unknown. Euclid is designed to investigate this mystery by studying how galaxies cluster and how the cosmic web evolved over time. The telescope can also use the distribution of galaxies to measure the expansion history of the universe. If those measurements agree with our current cosmological model, that strengthens the model. If they don't, scientists may have to rethink some of their assumptions. And that possibility is what makes Euclid so exciting. Not because it has already disproved our understanding of the universe, but because it gives researchers a powerful new way to test it. Some of the galaxies Euclid observes are billions of light years away. When we see them, we're not seeing them as they exist today. We're seeing ancient light that began its journey billions of years ago. The farther Euclid looks, the further back in cosmic history it can probe. That means a single survey can contain galaxies representing different stages of the universe's evolution. Nearby galaxies show us a more recent universe. More distant galaxies show us an older one. Together, they allow astronomers to reconstruct how the cosmic web grew from a much smoother early universe into the enormous structure we see today. And this is where things become truly fascinating. The universe began in a remarkably hot and dense state. Over time, tiny differences in density grew under gravity. Dark matter gathered into increasingly large structures, and ordinary matter followed. Eventually, stars and galaxies formed. Clusters developed. Filaments connected them. And enormous voids emerged between them. Euclid is giving scientists a way to study this entire process statistically across a gigantic portion of the observable universe. It can also reveal galaxies and structures that were difficult to detect in previous surveys. Some galaxies are extremely faint. Others are hidden among brighter objects. Some contain populations of stars that provide clues about how galaxies evolved. By observing enormous numbers of objects at once, Euclid can turn individual discoveries into a much larger statistical picture. That is one of its greatest strengths. It isn't trying to find just one strange galaxy. It's trying to understand billions of them. And when you study the universe at that scale, small patterns become incredibly important. A tiny systematic difference in the shapes of millions of galaxies can tell scientists something about the distribution of dark matter. A subtle change in how galaxies cluster can provide information about cosmic expansion. A difference between the predicted and observed growth of structure could point toward missing physics. This is why Euclid's data may become more important as the mission continues. The most significant discoveries may not be the most visually spectacular ones. They could be hidden inside statistics, correlations, and patterns that only become obvious after millions or billions of measurements are combined. And there is another strange consequence of this. The universe is becoming too large for humans to analyze by intuition alone. Euclid will generate enormous quantities of data. Scientists need sophisticated algorithms and machine learning techniques to classify galaxies, measure shapes, identify structures, and search for subtle patterns. In other words, we're building machines to observe the universe and then building other machines to help us understand what the first machines discovered. But the goal isn't to replace human understanding. It's to extend it. Because the universe contains far more information than any individual human could ever process. And perhaps the most humbling thing Euclid is showing us is how much of the universe remains invisible. Everything we've ever seen with our eyes, telescopes, cameras, and detectors represents only a fraction of what exists. Dark matter cannot be seen directly. Dark energy remains mysterious. And yet both are central to our understanding of cosmic evolution. We can observe their effects. We can measure their influence. But we still don't know exactly what they are. Euclid is therefore doing something deeper than simply taking photographs. It is testing the framework we use to describe reality. Every galaxy it maps becomes another data point. Every gravitational lensing measurement becomes another test. Every large-scale structure becomes another opportunity to compare observation with theory. And if the universe behaves differently from what our models predict, Euclid may help us discover where those models begin to fail. That doesn't mean cosmology is collapsing. It means science is doing exactly what it is supposed to do. We make a model. We test it. We find where it works. We find where it doesn't. And then we improve it. The cosmic web itself is perhaps the most extraordinary thing revealed by this kind of survey. Imagine zooming out far beyond individual galaxies. The Milky Way becomes a tiny point. Then our local group disappears. Galaxy clusters become dots. Eventually, even those dots become part of enormous filaments separated by gigantic voids. At this scale, the universe stops looking like a collection of individual objects. It starts looking like one interconnected structure. And we are inside it. Our galaxy is not isolated. Our solar system is not isolated. Even Earth exists within a much larger cosmic environment shaped by structures that began forming billions of years before our planet existed. That perspective can be unsettling. But it is also one of the most beautiful things science can reveal. Euclid isn't discovering a different universe. It is giving us a clearer view of the universe that has been there all along.